Welcome to the webinar about unit testing and code coverage measurement with Tessie. First, I would like to give you a very quick view of the company Hightex, the company I work for. Company was founded more than 40 years ago in Karlsruhe, Germany. On the right-hand side, you see our company building where I'm now located currently. Hightex is a part of the Infineon Group since more than 15 years. So we are 100% subsidiary of Infineon. We also have subsidiaries and partners, for instance, in the UK. We do a lot of things, for instance, engineering, production, consulting work. We are Auric's preferred design house, but the reason why I'm speaking here today to you is that we are responsible for sales, marketing, training, and first level support for the tool Tessie. And Hightex also provides test services by using the tool Tessie. Tessie is a tool for unit testing of embedded software, as you might know. So the test services mean if you have software that should be tested, for instance, to get a certification for a certain safety critical standard, you can give the software to Hightex and we test it, and you get it back tested and have not to do the work by yourself. Okay, so that's about Hightex. Now something organizational. During the webinar, you may ask questions using the webinar tool. I probably will not be able to answer these questions live online, but I will do my very best to answer your questions in the aftermath of the webinar by email. That's one thing, and the other thing is you will get the presentations that I showed today and access to a webinar recording later by mail. Okay, now we really start. Again, unit testing and code coverage measurement with Tessie. This session is divided in 3 parts. First, I need to talk a little bit about unit testing theory so that we know what we're talking about and what Tessie does, what is not visible on the user interface. Then in the second step, I will show you how code coverage measurement and unit testing works in practice. So we have a live presentation of Tessie, and concluding in the third step, I would like to give you a quick overview of additional features of Tessie, which I was not able to show during the live presentation, so that you know what Tessie is also able to do. Okay, let's start about a little bit theory. This is in another presentation. This presentation again is divided in 2 parts. First, I talk generally about unit testing of C and C++ programs. And then I explain in the second step what Tessie does exactly, so that you understand what will happen later on in the practical demonstration. Okay, the first question when we talk about unit testing is what is a unit? And this is depending on the programming language, in my opinion, and because we talk about C and C++ programs. So first, what is a unit of a C program? In my opinion, the functions or of a C program, the C functions are the units that we are testing during unit testing, and these could also be called modules, because depending on the standard you're working towards, you are required to do module testing or unit testing. But if you're testing C programs, the test objects for both kind of tests are the C functions. This is for C programs. So the question is, what if I program in C++? And this is shown here. If we have C++ programs, the test objects for unit testing or module testing are the methods of the classes. Having this, we can think of a software application as looking like this. Red rectangles represent the functions or methods or the units. Currently, they are displayed in red because they are not tested until now. The red arrows represent the calling hierarchy. And if we delve deeper into the topic, so we can think, what does unit testing mean for such a unit? And to answer this, I pick a unit which has a calling unit above and called itself another unit. So the question is, what does unit testing mean for the unit here in the middle of this calling hierarchy? And this is depicted on the next slide. Unit testing means the unit are tested one by one, comprehensively, thoroughly, and isolated from each other. Isolation can be at 2 points, at the point to the calling function, which is depicted here, and if the function calls itself other functions or units, there is another point of isolation. What is the advantage of this isolation? Sorry. The isolation to the calling unit gives you the possibility to work with arbitrary parameters. Look at this situation here where we have two functions, and function f2 is called from function f1, but only if the parameter which is passed from f1 to f2 is not a null pointer. And if you test these two functions together, for instance, during system testing, this would mean that you never will be able to check if the function f2 correctly detects that a null pointer is passed, and you never will be able to find out if the correct error number is returned. This is different during unit testing. It is technically quite simple to pass a null pointer to f2 during unit testing, and then you will find out if it is detected and if the correct error number is returned. That's technically very simple, and this is one of the big advantages of unit testing. This was the isolation to the calling unit. As I said, there's also isolation to called units in case the unit under test calls other units. And usually this call is replaced by a call to a so-called stub function. You can think of a stub function as a replacement for everything which should be called by the unit under test here. That means you do not even need the implementation of the called function, so you can make unit tests even if the software which is called is not implemented yet, and you are not dependent on changes in these called functions. So concluding, this isolation gives you a determinism. This means if a unit test now gives a certain result, it will give the same result if you repeat the test. That's because everything outside this blue line, outside the test object, is under your control and will not change without you knowing it. And the test object itself is under your control, and you will know if it changes. So after all, everything is deterministic, as this means you can repeat the tests, you have reproducibility of the tests, and this is a prerequisite for regression testing, which you need to do according to different several standards for safety critical application. And it's clear if you cannot repeat your tests, so the tests are quite useless. The blue line, which is depicted here, is called the interface, and the next page gives you a more detailed look on the interface. You see here in the upper part of the interface that it consists of the input variables, that's other variables that are read by the test object, and it consists of the output variables, that's other variables that are written by the test object. if the test object has a return value, of course, the return value belongs to the output variables. And of course, a variable can be input and output. Think of a global variable that is incremented by the test object. So first it is read by the test object, then it is incremented, and then it is written back. So it's input and output. This was the upper part, and I think the upper part was quite easy to understand. Please keep in mind that there is a lower part in case the test object calls other functions. The parameters which are passed from the test object to the called function or called unit are outputs of the test, and in case the called unit has a return value, this belongs to the input variable. So called function extends the interface. Okay, that was the complicated part. Now we see here the situation after the process step of unit testing. The units are now displayed in green, which means each unit each unit has passed the unit test, so each unit works as it should, but the errors are still red. That means we do not know after unit testing if the units work together correctly or not. This is checked in the integration testing process step. Now let's see how unit testing with Tessie works. We already know that the test objects are functions in the sense of C, or methods of C++ programs. So the first step by testing with Tessie is that we provide the C source module in which the test objects reside. Tessie analyzes the source modules and lists all the possible test objects, which might be C functions or methods. But what is more important is Tessie determines the interface of each test object, and we have already seen a little bit about the test object. We see here a simplified version of the interface. No called test objects in this example here, and the table here, the first two lines in the table, which are shaded in gray, gives you an example for a very simple interface. The interface consists of the direction of the variable, so the passing direction and the variables. So we see here an interface which consists of a variable A, which is input, and a variable B, which is input and output, and we have a variable C, which is only output, and our test object shall have a return value, which is of course output. So the first two lines depict a very simple interface. So data types are not shown here, so you also belong to the interface. The interface determines the structure of a test case. And a test case is depicted in the third line here in this table. So from the interface, we come to a test case by saying, okay, prior to the test, the variable A should have the value 5, B should have the value 4 prior to the test, and we expect that it has a value 8 after the test. And C, which is only output, we have only an expected value after the test, which is 17, and we expect that the return value of our test is 42. So that's how we came from the interface to a test case. This is a human task to determine how many test cases we need and which data they should have. After that is determined, everything else is automated. The first step which Tessie does is Tessie creates a so-called test application. And the test application is depicted here. The heart of the test application is the source code of the test object, usually the unchanged source code. which is here depicted in green, and the blue parts are generated by Tessie. It has its own main, so the test application is a standalone application. If you intend to run the test application on a certain microcontroller, the startup code for this microcontroller need to be added to the test application. And if the test object calls other functions and you want them to be replaced by stub functions, so the stub function code and such things are also automatically generated by Tessie. It is to mention that test data is not included in the test application. This means the size of the test application is the same for one test case or for 1,000 test cases. The test data does not, or increasing number of test cases does not increase the size of the test application. As I said, the test application is created as source code. So the next step is to compile the test application, and you can direct Tessie to have two basically different compilers. The first one is you can direct Tessie to use a native new GCC or G++ compiler, and then Tessie would compile the test application in a Windows executable, so an exe file, and the tests are executed completely on the Windows PC. The other possibility on the right-hand side here, you can direct Tessie to use the cross compilers that you use for your embedded project and compile the test application by using this compiler, which means the test application is compiled in a binary for the microcontrollers that you are using in your project. That raises the problem that you need an execution environment which is able to execute a binary for a certain microcontroller. Tessie usually uses a software debugger of your development environment as execution environment, and this software debugger can act as an instruction set simulator, for instance, which is depicted here on the left-hand side, underlined in green, or it can act as an interface to, let's say, a GTEC debugger or BDM debugger, and the tests then are run on the actual target hardware. Which possibility you choose for the compiler and for the execution environment is not really important to Tessie, but what is the difference is the relevance of the test. If you execute the tests using the native GCC compiler, which is of 32-bit compiler, and your actual target is 8-bit microcontroller, you might have some differences in integer sizes, maybe in the endianness, and so on. So the test relevance is rather low if you use GCC, and it is rather high if you use the actual cross compiler and you execute the tests on an actual microcontroller. So you can really rely that the test result, which is given during unit testing, is also later in the project the same result. This slide here shows again the difference between executing on the host and executing on the actual target hardware. In both cases here, as a cross compiler is used, Tessie communicates with the software debugger, and Tessie does not really distinguish between execution on the instruction set simulator, which means the complete tests are executed on the host, or executing the tests on the actual microcontroller on the actual target hardware. The debug system here is usually a JTEC debugger, microlink from Kyle, or JLink from Sega, or something like that. The only difference here is if you want to execute the test application on a certain target hardware, you need to make sure that the startup code and such things and the memory layout of the target of the test application corresponds to the memory layout of your target hardware and the required startup code. The next thing is execution of the tests. So Tessie loads the test application in the execution environment, and then a test is executed in basically 4 steps. The first step is the test input data is transferred to the test execution environment. In the second step, the test is actually executed, and in the third step, the test results are fetched back from the test execution environment, from the RAM of the target hardware, for instance, back to the PC, and then in the fourth step, Tessie compares if the expected result is equal to the actual result or not. If yes, the test has passed. If no, the test has failed. And in case the test has failed, you can use some features of Tessie to debug this failed test case. Tessie is able to execute a single test case, what is quite simple, but Tessie is also able to execute a test case with a breakpoint at the beginning of the test object, and this means this test execution with a breakpoint will stop in the debugger in the execution environment, and this allows you, the combination of these two features allow you to debug failed test cases. Okay, this was the theory part. Now we come to the live demonstration. You see here now the graphical user interface of Tessie. You might recognize that it looks like Eclipse. This is because Tessie is based on the Eclipse-rich client platform, and this means we have the perspectives. Currently, we are showing the overview perspective. A perspective groups the views, for instance, the test project view or the console view, which the manufacturer thinks is necessary to fulfill a certain task. We have other perspectives. For instance, here is a requirement management perspective where you can specify requirements, import requirements, and link them to test cases. What we will not see in this presentation here, we have a classification tree editor perspective where we can specify test cases according to the classification tree method. We also will not see this here. The scenario editor perspective is used for integration testing, and the script editor perspective gives you a graphical representation of the test cases, also not planned for this session here. What we will see is the interface editor, the test data editor perspective, and later the coverage viewer perspective. Okay. In the test project view here, you see some test cases that I have already defined. Usually this view will be empty when you start Tessie for the first time. In this view, the test cases are organized in a tree-like structure, and the root of this tree-like structure is called test collection. And I now create a new test collection, and I can also give it a name. And below this root, we can have an arbitrary structure of folders. I just make one folder, I give it a name, and the leaves of this tree are usually the Tessie modules, and I create now a Tessie module as a leaf, and these Tessie modules are connected to the CSource file. So the structure of this tree roughly corresponds to the layout of your source code directories. Okay, before we proceed, I would like to ask you a question, because I would like you to ask about the programming language of the example test object that I would like to use, and it's up to you to decide which kind of programming language you want to have. So poll is ongoing, and I think now it is quite stable. So I close the poll and I also show you the poll, and you see that C has won. So most of the of you want the test object to be in the C programming language, and this is and I hide it now. I have a second poll. You can also select if we shall use the GCC compiler for compiling the test application, or if we shall use an embedded development environment. We have the selection between the Kyle MDK for Cortex, for a Cortex microcontroller using microvision as a debugger, or we can have an AR compiler, in this case for the MSP430 microcontroller, using CSPI as debugger. And I think the results are now stable, and I show you the results of the poll. That means we use native GCC compiler and the debugger, which is built in Tessie, as execution environment. Okay, I hide now the polls, and yeah, this means we select the compiler. The GCC compiler which you have chosen is the default that you can also use if you have an evaluation version of Tessie without any cross compiler. And the next thing is that I have to select a C source file in which the test object which I want to use is in. I select the file isValueInRange.c, and I would like to show you the contents of this file. I can edit the source code file, and you see we have here a very simple C source file with only one function in it. The function is value in range, and this function solves a very simple problem. It shall find out if a value is inside a range or not. For instance, if the start value of the range is 5 and the length is 2, so 4 is outside the range, it's before the range. 5, the start value itself, is inside the range. 6 is inside the range. 7 should not be inside the range. But due to a programming defect in this test object, if I use the values 5, 2, and 7, the wrong result is returned. So I have a test case that will fail. So structure is given as the range is given as a structure with two components, start value and length, and the return value is a result. It is an enumeration type having two possible values, yes and no, which obviously mean yes inside the range and no, it's not inside the range. As I said, a very simple test object. Okay, so next thing is now I let Tessie analyze this C source file, which means Tessie lists also functions that are inside the C source file, which is only one function in our case, and Tessie also determines the interface of this test object. We see here the list of possible test objects. Only one is value in range, our function. And if I switch to the interface editor perspective, I can see the interface which Tessie has determined for this function. And if I do so, I see here because it's a very simple test object. We have no external functions, no other function in the same C source file. We have no external variables, and we have no global variables. We only have two parameters, and the first parameter is a structure. It has two components, the start value and the length. And the important thing here is that Tessie has determined that the passing direction of both components is in. In means these variables are only read by the test object and not written. And I think it is clear, if we want to find out if a value is inside the range, we need to provide the values of the range prior to the test. And the same thing is with the second parameter, the variable v1. V1 has also the passing direction in. It is a value that we want to know if it's inside the range or not. So we need to specify it prior to the test, and therefore the passing direction is in. And Tessie has determined that v1 is not written inside the test object, only read, therefore in. The passing direction out is here for the return value of the test object. Sorry for the interruption. So the passing direction out is for the return value of the test object. I think it's clear that this needs to be out, and it is a value of the enumeration type. Okay, as said, the interface determines the structure of the test cases, and the next step is that we define some test cases. We do so in the test editor, test data editor perspective. We have here on the left hand side a view which allows me to create new test cases, and if I select new test case from the context menu, I will get a column in the test data view on the right hand side. So I select new test case, and this gives me a column here on the right hand side. And this column is used to specify test cases. The upper part of this column are the input variables, and the lower part are the output variables, and the yellow fields show me where I have to specify values, and I start by using the value 5 for the start value of the range and the value 2 for the length of the range, and I want to know if 6 is inside the range or not. And Tessie proposes, suggests the two possible values for the return, and in our case, yes is the correct expected result for the first test case, and I save this test case, and then I'm able to, for instance, copy this test case and paste it, so I get a second column, a duplicate. I can change in the second column the value which we want to know if it's inside the range or not, and according to the specification, 7 here should not be inside the range, so the correct expected result is no. But as I told you, due to a programming defect in the test object, this second test case will fail. And if I click on execute tests, Tessie will execute both test cases, which means Tessie will create a test application with a test object inside and compile it using the GCC compiler, compile it to a Windows executable, and execute the two tests using this Windows executable. And then we should see the results. Okay, we see now the two results. The first test case is displayed in green, so this means it has passed, and as expected, the second test case failed. We do not get our expected result, we get yes as result, as expected. At this point, I would like to quickly show you how easy it is to generate a test report. Test reports can be in PDF format or HTML format or Word format, and I have selected HTML at the moment. The advantage is that I can easily increase the size, so you can see that we are, it's 933, and we have some management information, but the main thing is that we have here the values of the two test cases. Very simple at the moment. The test cases have no name, no description, no specification. We have no test case specification according to the classification tree method. So it's a very, very simple test cases. What we see, the first test case has passed with this green tick mark here, and the second test case has failed. We see the input values 5, 2, and 7, and the actual value is yes, but we expected no, and it was not equal, and therefore the test failed. Very, very, very quickly. Okay, our problem now is that the second test case has failed, and I told you that Tessie has the possibility to execute a test case, only one test case. And the second thing is that Tessie is able to set a breakpoint at the beginning of the test object. This is done by taking this tick mark here. And if I execute now the second test case, the test will not run until its end, but we will stop in the built-in CDT debugger, and then we are able to debug this failed test case. As you see, we are now here at the beginning of the test object, and you see that the values are 5, 2, and 7, and I can do line steps. And yeah, I would expect that return no in line 43 is executed, and yeah. But if I do another line step, I see, okay, I get the return yes, the wrong result. And the reason is a missing equal sign in the decision of the second if. So yeah, if I have an assumption what could fix the problem, I can run the tests to its end. And yeah, by the way, if we had selected an embedded development environment, we would not stop in the CDT debugger, but for instance in Microvision from Kyle or in CSpy from AAR. Okay, we have the assumption that an equal sign would remedy our problem. So I can insert an equal sign here. I save the source file and I go back to the test data editor perspective and I rerun the second test case, but without checking defined breakpoint at test object. This means the test runs until its end immediately, and I expect to get a green result because of the fix in the source code. Yes, that's like I expected it. The second test case now passes, but actually I have only executed deliberately executed only the second test case because to show you that we do not know at the moment if the first test case will also still pass, but we can easily check this because we have test automation in place now with Tessie, and by clicking on this execute test button here, I execute all the available tests, and this can be used to check if the first test case still passes with a change in the source code or not. And I click on this button here, and so I will see if the first test case is disturbed by the equal sign, and happily, luckily, it is not. So both test cases fail now, pass now. The concluding thing what I want to show you is how code coverage measurement is done with Tessie, because we have now two past test cases and we should find out what coverage we have reached, and it is very easy. I can say execute the test cases, but in this case with instrumentation. Instrumentation means code coverage measurement. Tessie instruments the code now, which means also that you have to do the functional tests without instrumentation. I have pre-selected that we want to measure branch coverage and modified condition decision coverage. And if I click on execute, Tessie now instruments the code, which means counters are inserted and such things. And then the two test cases are executed and we will see if we reach 100% or not. And here on the left-hand side in the column C1, we see the branch coverage, and we see we have only reached 75% branch coverage. And in the column MCDC coverage, MCDC, we see that we have also only reached 75% MCDC coverage. And if we want to know the details about this, we can switch to the code coverage viewer perspective. And if I do so, I see a flowchart of my test object. And I see also the source code of my test object. And yeah, I see red parts. I have, for instance, here a red branch. And if I click on this red branch, I see that it corresponds to the return no, so to the send branch of the first if. And I can also click on the decision itself. So I see the first if always was evaluated to false. So I never had the true. And I see here the decision was the start, the value v1 should be smaller than the start of the range, so we never had that situation. We see here in the flowchart, so yeah, the accumulated results of 2 test cases. So 2 test cases took the then branch of the first if instruction, but then in the second if instruction, 1 test case took the then branch, 1 test case took the else branch. If we want to know what, for instance, the second test case, the path of the second test case is, we can simply select only 1 test case, and now we see the path of the second test case. And if we click on the green arrow here, the green branch here, we see that it corresponds to the then branch of the second if instruction. And yeah, the second test case should execute this return no. That was the reason why we inserted the equal sign in the decision of the second if instruction. So everything is consistent here. This was the last thing that I wanted to show you in a live presentation. As I said, the concluding part of this presentation, this webinar, is here to have a look on some additional features of Tessie, which I was not able to mention during the webinar. Sorry. First thing is, Tessie has a certificate from the TÜV Süd in Munich, and this states that Tessie is suitable for to be used in development of safety critical application. The certificate covers for safety critical standard 61508, 26262 from the automotive area, 50108 from the railway area, and 62304 from the medical area, but you can use Tessie also for other safety critical standards like 13849 or whatever. In case you need to qualify Tessie by yourself, a tool qualification package is available, which allows you to get your own confidence that Tessie works correctly, and you will not have a past test case in your test report if it's actually failed. As I already told you, Tessie covers the 2 steps of the V-model integration testing, which we have not talked about until now, and the process step module testing or unit testing, depending on the standard you are working for, or you call this process step. And about integration testing, integration testing is in Tessie called component testing. The test object for integration testing are components, and they consist mainly on an assembly of units, several units which are working together. And this is depicted here. So the blue rectangles depict the units. And a component also consists of data, and you can stimulate such a component. And and the component usually is a part of your application. It's not a complete application. So there is also the possibility that you use stub functions and so on. So please keep in mind, Tessie can also cover the process step integration testing. As I already mentioned, Tessie has also the possibility of requirement management. Tessie contains a complete requirement management facility, so you can create requirements, you can link requirements to test cases, and you get reports if all your requirements are linked to test cases or not, and if these test cases has passed or failed or not, and so on. You can also import test cases requirements to Tessie. Tessie supports different formats, several formats, for instance, CSV files, what you see here, but Tessie also supports requirements interface format and requirements interchange format, regef, and probably your requirement management tool, which you are using, is able to export the requirements in requirements interchange format. Tessie also supports test case specification according to the classification tree method. Yeah, this is a graphical method. You draw a classification tree, which is the upper part of the specification here, and the test cases are specified in lines in this test table below this classification tree, and the markers, which means the bullet points here, select from which classes of the tree you select values for the test cases, and this also shows you what is the meaning of a test case, what should be tested in such a test case. And you see also by the tree if invalid values are used, if boundary values are used, and so on. And a basic thing here in this classification tree method are equivalence classes. You see here, for instance, that the thing which is called steering angle is divided in 3 equivalence classes: left, central, and right. Unfortunately, it's not enough time to explain this method in more detail. Just an idea how such a test case specification looks like. And Tessie is also able to display test data graphically. We see here a graphical display of 20 test cases. The input is given in this page. It's a step curve here, and you see the output. The results are in blue and green. The expected results are in blue, the green are the actual results, and you see that for most of the test cases, actual and expected are equal. Only for 3 test cases there's a slight difference, and this is more easily visible in graphical displays than in looking at the numbers. So just quick mention of this. I told you about the script editor. As a script editor is a textual representation of the test cases. This allows you to store, for instance, test cases at a certain point in time and compare the test cases with the test cases you have a fortnight later, and you see what has changed in your test cases and whatnot. If you also could, yeah, write your test cases using this language, but I don't recommend this. It's too complicated, I think. Tessie is also to be run without a user interface, so there's a command line. You can write your batch scripts to control Tessie, so Tessie can be run without user interface in the so-called headless mode. And this command line language is quite useful if you want to integrate Tessie with continuous integration mechanisms like Jenkins or so on.